Oh, welcome everybody to another edition of the Thursday Critical Canadian Building Science webinar series. Imagine everyone's ready for the holidays, so we appreciate you taking a little time today to sign into some building science info. We'll give folks just a little bit of time. I see there's several more still coming online there, so we'll give just a few more minutes. Again, always good to see familiar names on here. Coming on. Today's session's definitely about a technology that's well known in certain areas of Canada and the US, but in many ways poised to actually be better known as we look ahead. And I think that's what we're going to be talking about today. So I think we'll go ahead and get started. So thank you everybody for attending today. My name's Andy Oding of Building Knowledge Canada. Today is the Critical Canadian Building Science Series webinar that focuses on drain water heat recovery combined with net zero ready homes. And when we talk about net zero ready homes, these could be zero energy ready homes out of the US. They could be net zero ready homes here in Canada, either one. We're talking about homes that are going to be built to future building codes. You know, here in Canada, it would be sort of tier 4, 5 of the National Building Code. In the US, it would be homes that are built similar to the 2021 IECC or a little bit more. So welcome to today. Agenda, we're going to do some introductions. We have our sponsor with us today, Enbridge. So Michelle Nicotin has joined us. We're going to have Michelle come on here in just a minute. We will then have our drain water heat recovery experts walk us through this technology. It is interesting. I'll just make a note. It's interesting to see technologies like this that are entirely passive. So no moving parts, no mechanical mechanisms, just passive technology. So that gets us a little excited. The next thing we're going to do is Nick Ballarin, part of our building science team here at Building Knowledge Canada, has actually done a little case study on a home. So he's going to show us some modeling results, both on energy, carbon operationally and embodied, and on cost. And then we're going to try to leave you folks a little bit of time for some Q&A at the end of the day. Couple of things on housekeeping. Keep in mind, if you have questions that are technically related to the content, please put them in the Q&A. Do not put them in the chat. The chat should be left for if you're having issues with the Zoom LinkedIn or something like that. Stacy Cooper, our Building Knowledge Canada colleague, is looking after that in the background, and she can help you there. The other thing too is just remind you, as good Canadians, be considerate, be thoughtful, be respectful. This is a nice, friendly space to challenge and yet think deeply about what we need to do to move forward into the future. The webinar is recorded. After the webinar today, the recording, as usual, will be sent out. You're welcome to use that, share it with your teams. It'll also reside on our YouTube Building Science channel, and it's good information for everyone. We'll do a survey. We'll just ask, the only thing we'll ask out of this today is that you do take a little time in the survey. They are helpful. And just a note for some of you, if important, the closed captioning is enabled as well too, so you're welcome to that. So Michelle, welcome, and thank you again for supporting this.
Thanks, Andy. Hello, everyone. Just like to say thank you for having me here today. I just want to start off with a quick land acknowledgement. We're acknowledging the land on which we gather in the traditional and historical lands of the original people of Turtle Island, who have been the caretaker of these lands since the time immemorial. Today, this gathering place is home to many First Nations, Métis, and Inuit people. Our acknowledgement of this reminds us that our great standard of living is directly related to the resources of and a relationship to Indigenous people, and we have the responsibility to honor that. So we always like to start all of our meetings off with a land acknowledgement. I will get right into the slides because I'm really excited to share with you a couple of our programs that Enbridge is offering this year to the builders in Ontario. Andy is very familiar with the two programs that we have that are through the Savings by Design. The first one is our Energy Star for New Home program. So this one is across Ontario. It's within certain municipalities. So the only caveat to this one is that you have to send in an application, and then you get it approved from somebody from our team. And then once it's approved, you can submit up to 50 homes within the calendar year. So anytime between January 1 and November 30th. And you can get $1,650 per house, up to 50 homes within that subdivision. So these are for Energy Star or equivalent. You do not have to be building with natural gas. So I always get questioned on that, but it is just it's an energy transition program to help alleviate some of the costs of getting your houses to that next level. The other program that we have is our Net Zero Energy Ready program. So this one is for builders also across Ontario, also not having to build with natural gas. And you get $15,000 towards that next step. So getting the house to this net zero ready. And then you also get money value in all the training that you receive from your energy evaluator, and marketing pieces, sales tips, all those kind of things of trying to help build or help sell your net zero discovery home. Andy's very familiar with these, so he always takes lots of questions, and it's been a great program. The Net Zero Energy Ready program sold out last year because we only have enough room for a selective amount of builders in the calendar year. And so that one is always a first come, first serve. And then the Energy Star, the last program, we have lots of room. So we try to get that one out to as many people as we can within Ontario. So.
Awesome.
And
Thanks, Michelle, very much.
To get the applications, sorry, Andy, to get the applications too, you would reach out to your local Enbridge rep. So I know that Stacy and team send out the presentation after, and I have included a little blurb in there of who the reps are within the regions of Ontario, so you know who to reach out to, and it has their phone number and their email address. So.
Awesome. Thanks, Michelle.
Wonderful.
Yeah, we are getting inquiries already about both of these programs. I know, like you said, the Net Zero Energy Ready program, you sort of put unlimited resources on designing that discovery home, and I know it fills up every year quickly. So good. Okay. Well, thank you. Thanks again for supporting us. Okay, let's move into some polls. We always like to find out where you folks are from. So get your Zoom fingers ready. Give us a little sense of where you're located. It's always good for us to know. Looks like we've got some coverage right across most of Canada. Isn't that cool? Very good. Excellent. Atlantic, Ontario, Manitoba, British Columbia folks. Excellent. Good to have you with us. Excellent. Let's go on to the next question, maybe. And that is, what is your occupation? What keeps you busy? It's always interesting to see who attends these sessions with us. Some engineers, architects, lots of builders, lots of renovators and developers all together, some energy advisors, raters, consultants, sales reps, site supers, folks that actually have to build the house. It's always good, right? We often say as engineers and designers on that side, it's one thing to design and engineer something. It's a whole nother thing to actually have to build the thing. So, all right. Well, thank you very much. That's excellent. Okay, let's get you into introductions. Again, Nick Ballarin is going to be joining us later on doing a presentation. So Nick's been with us for a while. Nick's a graduate of Humber College Sustainable Energy and Building Technology program. Nick has been doing a lot of work with our builder clients, both in the US and Canada on the carbon side. And so he's taken a little bit of his time today to help us with that as well too. Dylan, good to have you. Yeah.
How's it going, guys?
Good. So Dylan, you're business development manager, EcoInnovation Technologies. Dylan We've known Dylan for some time, just Marc and the rest of the team, and they're always good to keep us up to speed with how the technology is advancing, but also where they see applications. I know one of the things that we have found, Dylan and Marc, and Marc's going to be doing the presentation today, is that both of these gentlemen have been very, very helpful to ourselves and to builders and developers early in that design stage when you're trying to figure out how do you fit a technology like this into a complicated plumbing scheme, right? Multi-family buildings, multi-levels, can it be done? And I'm hoping, and I think you are going to give us some direction on that today. So, Marc, great to have you. Marc's co-founder of EcoInnovation Technologies. Marc's, there's his biography. We'll be sending that out with everybody. Marc, it's good to have you. We'll make sure
Hi,
your speaker's
everyone.
working okay.
Great to be here. Thank you.
Good, good. So Marc, I'm going to stop sharing and you take it away and let's get rolling.
Okay, let's try this.
While you're getting set up there, I'm just was going back in time a little bit. I remember the first drain water heat recovery unit that I ever was involved putting in a home was like in 2005, 2007, something like that. And I just anecdotally, I remember we did about 200 homes with drain water. And of course, when we tried to figure out how much money it saved, no one really knew how much money they spend on utilities, right? Nobody really thinks about that. But the one thing I do remember is that on those homes, we didn't have one single issue where the homeowners didn't have enough hot water.
There you go, for sure.
That's sort of cool. So
We'll talk about that a little later today.
very
Some of
good.
the benefits that come on with rainwater heat recovery. So I'll just start with, so my name is Marc Fontaine. So I'm a co-founder of EcoInnovation. We have the thermal drain product line. So we've been in business since about 2008. And we're a manufacturer of rainwater heat recovery. So we design and build our units. We're based out of Montreal area, and we supply these devices across Canada and parts of the US. So they're widely available. Um, Rainwater heat recovery has been around in Canada since roughly the 2000s, some along those lines, and has evolved through that time. And basically, when rainwater heat recovery ended up in the Canadian commercial market, um, NRCan and other interested parties started to notice this new technology that nobody knew anything about, and some studies were put together and on model homes and real life applications and whatnot. And then a little later on, CSA recognized that there needed to be some sort of a standard for this technology. So came about a couple CSA standards, so the B55 1 and 2. And then, a little later, some utilities got interested in this with some programs, and then there was some code adoption in certain provinces and code references in many provinces and states. And now I guess we're a bit more mature technology, relatively widespread and well known for some installers, which was not the case if you take it back 10 years ago. And so we're sort of prepping to look into the future of what rainwater heat recovery can do for everyone here. And so not only has rainwater heat recovery um, was made more gained some awareness through time, it also changed quite a bit. So um, rainwater heat recovery today costs less than it did 10 years ago, even with inflation and all of that. It's a technology that has evolved quite a bit. Our thermodrain product is a fourth generation, so it's been revised many times in terms of efficiency and performance. And as I mentioned, cost has gone down. We're usually looking at 4 to 8 years in a payback period. So that just gives an idea of where we're at today in 2024, and getting ready for all the challenges that the building industry faces in the upcoming years. So we'll talk a little bit today about you know, what drain water heat recovery can do for in energy efficiency programs, Energy Star, HERS rated homes, MLI Select home, um, for code compliance, some increase in mechanical systems performance, and things of that nature. So let's get it going.
Awesome. I think before we start, though, quickly, we'll jump in and we'll ask people if they've ever used drain water heat recovery before.
Very nice. I imagine there's a few.
There's got to be a couple, especially people
Yeah.
from Ontario and Manitoba. I think we got a couple in the group.
Good. Look at that. Actually, that's an interesting split there. Good.
Oh yeah, you're right. Right down the middle.
Yeah, very good. Excellent. Thanks, Stacy. That's good.
So I guess we'll touch base on a few different things, and for those who know more about this, might be a little bit of a refresher. Some people who know nothing of it, I'll get a little bit more information. So basically, drain water heat recovery is kind of what it says. It's we try to recover heat from any hot water source that's sent down the drain. So our typical application, which uses the most water and energy, is a shower. So imagine you have water going down the drain when you're taking a shower. So that's where we want to try and collect some of that energy back from the heat. So here you have a basic device, which is a all copper construction. So you have a copper central tube, that's the drain tube. You have a copper winding around that central tube, which is where the cold water is going to flow. And basically what you have is hot water coming down the drain, heating up the inside of the copper tube. As we know, copper is a very good heat conductor. So that heat is going to migrate through the material and is going to come and heat the inside of the coil portion. The coil portion, we have cold water coming in. As it makes its way around that coil up the unit, it gathers some of that heat from the copper, heats up, and comes out preheated. So that's basically the working principle of these devices. So as Andy mentioned in opening, it's a passive device. It's a device that only does heat transfer. There's no communication between the drain water and the potable water in the system, and there's also no moving parts or mechanical seals and that kind of stuff. So this is how it works. Drain water heat recovery is usually installed vertically, and the reason for that is that as water flows down the pipe, a vertical pipe, instead of basically trickling down, it forms a film inside the pipe, so it has a tendency to spread out and then wet the whole inside surface of the pipe, and that forms a relatively thin film of water, and that's how we can be very efficient in transferring heat from the water to the copper tube inside. If we only had a small trickle on one side, then that would make the surface area for transfer very small, and then we would not be able to reach the efficiencies that we're able to reach currently. Now we get this question all the time, so I'll get it out of the way. Vertical installation provides high performance. Horizontal or angle installation is possible in terms of usage. There's no problems doing it that way, but you lose 2/3 of the efficiency. And so therefore there are some applications, mainly in specific commercial applications, that we might go that route for energy savings, but usually is not something that we use in the residential building. So now that we've talked about the device, so the device collects heat, transfers it to the cold side, and the cold hot side preheat. So what do we do with that preheated water, basically? So this is a schematic that shows, I guess, the principle of operation here, where you can imagine you have a shower which is in use, and then sending hot water down the drain, which is a gray line, and going out the house. So on that gray drain line, what we have is a rainwater heat recovery device installed, and we basically feed the inlet of the winding we saw earlier, the coil, with cold water, and as that water goes up the device, it heats up and preheats and becomes lukewarm basically. And then we use that preheated water and we send it to the inlet of the hot water tank. So this is a very common application. It's probably, I'd say 60% of the installations being done out there are of that nature. We do it this way. And so obviously the hot water tank receives warm water instead of cold water. So that's how we re-inject the energy that we captured into the system. So there's a few ways of doing this that we'll see a little later, but this is a very typical way. It's to note that in this diagram we showed a shower. The rainwater heat recovery unit can have any sort of water go through it. So we can hook it up to the whole bathroom, including the toilet, sink, if there's washing machines, etc. It's not limited to the shower. Obviously, the shower is the device that produces or uses the most hot water in the home, but there's potential for some benefits with like a kitchen sink, for instance, where there's a lot of rinsing going on and so forth. So this is information that you guys probably know better than I. So hot water is roughly 20% of the usage, and as homes become more and more energy efficient, obviously it becomes more of a percentage of that energy load. And there isn't a lot of technologies that address hot water. I mean, there's obviously hot water heating systems that address this, but there's really not that many out there. And so we think that rainwater heat recovery is a good way to address part of that. It's not a whole solution, it's part of the solution. So some of the things we touched base already is that since it's a passive device, it's an all copper device, it has a very long life cycle. So 30 to 50 years is something that we should expect out of it. There's no maintenance to it. There's no cost of ownership to the end user. It's always working. If you've got hot water going down the drain, it's going to do its thing. There's no waste from replacements of parts, of components in servicing, or replacement of the unit after a certain period of time. So there's no costs or waste from this device moving forward. So low embodied carbon, we feel it outperforms many of the mechanical systems that we may put that need that servicing, cleaning, or parts or replacement after a certain period of time. So some of the things that are interesting is rainwater heat recovery. I mentioned the cost today is less than it was 10 years ago. In most scenarios, you can get away with a rainwater heat recovery unit installed in a home for about $600. Now that varies a little bit on the model. So I would say it kind of starts there on the model, on the type of the size of the builder, how many homes they do a year, and what the objectives are for the energy savings they're looking for through this device. But that gives an idea. And it's kind of a set and forget it kind of device. So you put it in, there's no starting process or adjustment or hookups that need to be made aside from the initial install. And so once it's there, it does its thing for the future. As I mentioned, it's manufactured in Montreal. It's all copper, so it's 100% recyclable. It's probably worth more when you recycle it in 30 years than it is today. And then obviously it provides savings through the greenhouse warming potential of about 200 kilograms CO2 equivalent per year. Now that varies a little bit. There's models that may be more, maybe less, depending on your source of heat also. So that needs to be looked at. So what rainwater heat recovery can do is it can come in and help in different ways. So obviously, in terms of hot water heating systems, so it's in combination, increases the performance of that. And then the performance of the devices, any manufacturer in Canada makes has been verified under the CSA standards. So we send units out, they go to, in our case, it's Intertech. They measure the efficiency of these devices under the CSA standards that I mentioned earlier, and then they give us the results, and then that's what's published in our marketing materials. Those results are also sent to Can, who also publishes these results. And those are the numbers they use in the HOT 2000 software for evaluation. So water heat recovery helps, as I mentioned, in water heating performance. So it works with different appliances or types of water heaters, and it also improves recovery. We'll talk about that just now. So water heat recovery can be installed with any type of hot water heating system. So tankless, gas, electric, hot water heat pump, electric, tankless, etc., etc. So let's talk about a few of the popular options here. So if we're looking at the tank, with the electric tank, the recovery rate is fairly slow on these devices. So water heat recovery essentially provides roughly 3 times more hot water from that storage tank. So I'll give an example. You have a storage tank that provides 20 minutes worth of hot water in your application. Then if you combine a water heat recovery unit to it, then you move from 20 to roughly 60 minutes of capable supply. And one of the regions, just to give an idea of what that does, is a water heat recovery unit will supply maybe at around 8 kilowatts of energy into the hot water tank. And a typical electric tank has a 4.5 kilowatt element on it. So you're basically twice as more energy being reintroduced in the electric tank than what the electric tank can supply itself. So that's a big advantage in terms of comfort. If we look at other advantages aside from the energy savings aspect, is that, you know, if you have a tankless electric water heater, you get that benefit. On gas, obviously gas has a lot more energy input initially. So usually if the gas is sized maybe a little bit undersized, that could be an advantage. But if it's sized properly or up, that should not be much of a help. It increases. We have a table here which shows some increases in flow rates when you have instant gas water heaters. So obviously the temperature, especially in the winter, coming into a tankless is what is your kind of critical design criteria for a given flow rate that require. So we have some examples here of how you can increase the flow rates of that tankless hot water heater when combination with the thermodrain. So, you know, if we look at an example of the 45, this 55 degree Fahrenheit and mid efficiency, and you have a 200 kBTU unit, then you go from 4.7 gallons a minute to 5.7. I say gallons per minute, I'm sorry, it's liters per minute. So that's an idea of what that does with that. If we look at hot water heat pump water heaters, they also have a combining effect with these devices. So you see in this table, the total input energy that's required with or without drain water heat recovery. One thing to note is that, and we'll see that a little later, but there's ways to basically pipe the preheat water from the drain water heat recovery to either a hot water tank inlet or to a cold side of a fixture. And depending on how you do it, there's advantages of doing it different ways when you're using a heat pump water heater, which will provide more savings. So these are things we can look at more in detail if you have applications that you want us to go through. Just to try to get, I mentioned energy earlier, how much energy a drain water heat recovery unit can inject in a system. We'll look at temperature, so that's another way of maybe getting our heads around what that does. So here you have a typical 42% efficiency unit, which is a very popular model. You have drain water going in at 100 degrees Fahrenheit. And then you have a cold water coming in at 50 degrees Fahrenheit or 10 degrees Celsius, which is an average temperature in probably Montreal, Toronto. And then you see the temperature increase coming out at 21.7 degrees Celsius or 71 Fahrenheit. So that's an 11 degree Celsius increase in the temperature of the water. So obviously 20 degree water versus 10 degree water is not the same, and therefore you see the energy gain when you go in and put that in a water heater. We have another example here with a 63% efficient unit, so that would be on the high end of things. And so we have the same scenario here where we have a 10 degree inlet, a drain at 37, and what we gain is it would go to 27 degrees Celsius. So now it's a 17 degree increase, and that's 10 kilowatts of energy being reintroduced in the system, which is quite large, quite large. This is just, again, give some perspective of what drain water heat recovery does in a whole system. So obviously it reduces peak load because, you know, the hot water is being used at different times of the day where other appliances are also being used, so mornings and evenings. And so this is a study that was done by Hydro-Quebec that shows with drain water heat recovery, there was a 10% reduction in heat load. And I mentioned earlier 8 kilowatts, 10 kilowatts going back in the system. Well, obviously that's not coming out of the utility during a certain period. So that was a study they performed, and they had another little something here about overall reduction over, you know, 1.2 million units installed. Just to give, again, perspective here. So I believe we have a poll question coming up.
Nope, you're on mute, Dylan.
Yeah, what type of builds do we typically do? So
Good.
we'll see what we got.
We'll let as folks sort of fill this out. Marc, this is really interesting. You know, bad on me for not really looking into these details. And you folks, I mean, these are details and studies you've had for a long time. But, you know, we're now encountering challenges with peak loads on the grid, and everyone's concerned about that type of thing. And, you know, we're concerned about electrification and how the general public is going to deal with it. And yet here are these simple technologies that sort of help shave the edge off from that.
Well, again, you know, we drain water is not a problem solver for every situation, but
Right.
it's something that moves us forward when maybe there's not a lot of other options to work. And as I mentioned earlier, they work when there's a demand for hot water, right?
Right.
And so obviously they're not in use when we don't use water, but when we do, hot water, pardon me, when we do, that's where it kicks in and does its thing. So obviously mornings and evenings is where we see the most benefits.
Yeah. I find it interesting too. I'll just make a comment and then we'll take a look at these projects, is that we find in our work with you know, low load communities, efficient homes, efficient buildings across all the US and Canada is that it's one thing to design devices that heat water or air that are efficient. It's another thing to design distribution systems that make it efficient, right? So, and that's something that you know, here in Canada, we only see that a little bit. Whereas in the US, as you would know, not only are there guidance in, say, the Zero Energy Ready program for efficient water distribution, it's actually you have to have limited amounts of hot water standing in pipe, right?
Mhm.
And I think that's something we're going to start to see more and more here in Canada is, yes, it's good to have good, efficient developers of heat and hot water, but then you have to have good, efficient system design. And that's what you're sort of part of. So that's cool. Good. So looks like we've got a lot of single family and townhomes attached. Got some MERBs, so some unit over unit type product. Does this sort of run true to what Dylan, you and Marc also see?
Yeah, this is typically the kind of yeah, percentages we see when we get builders. Yeah, we'll have predominantly single family home with some urban condo use as well.
Okay, good, good, excellent.
I think there's something maybe interesting here because as we just mentioned, we do a lot of I guess detached home and townhouses, that kind of stuff. But there's interesting things with MERBs too. So we've been working a lot in the last couple of years because the CMHC MLI Select has a program for small buildings. So what we would call a plex here, maybe in Quebec, and stack in elsewhere, potentially where you have a few levels. So there's a point system here that provides incentives for the builder I would say financial incentives. So we've had a lot of inquiries about increasing of ways of getting these points, and increasing the energy efficiency of the building is obviously I would say most common, because obviously the builder has something of an advantage if he can reduce his energy load. And so we've been doing a lot of buildings for shooting for 40% reduction in over NECB.
Right.
Pardon me, NECB. And so I'd want to talk a little bit about this today. I think that might pique the interest of some of you guys out there.
Absolutely.
So so we have an example here of basically a 6 dwelling unit. So you have basement dwellings, ground floor dwellings, and a top floor dwelling. So this is a case study that was done here by a firm that does energy audits. And so they were nice enough to share their data on this project. So we had this building using energy guidelines of with a number of showers, 2% occupancy, which is fairly low versus maybe other types of dwellings. So 7.6 liter minute shower heads. So we proposed a rainwater heat recovery system with a nominal efficiency of 46% in their installation. And so the savings are 695 kilowatt hours a year per dwelling. And so when they put that in their model, since rainwater heat recovery is installed in the basement and is servicing the levels above, you have 4 out of 6 dwellings being serviced by rainwater heat recovery. And I'll touch base on the installation just in a few slides. And so for them in their project, that was a 6.2% reduction in their energy usage. So out of the 40% that they were looking to get, they had 6.2% that came directly from rainwater heat recovery. Now in this building, that's 2 units being installed. So it's a fairly low cost approach to get those points. So we've had a lot of success in the last 2 years with builders doing these types of projects that thought that rainwater heat recovery is a good value. And so I would encourage anybody who's doing that to maybe have a look at that and see if that makes sense for their type of building.
Mhm.
So I mentioned, installation a little bit. So we're going to try to move into, from what the device is, what it helps to do, and how it actually installs. So here we have a single family typical um, uh, home where we have potentially a basement and a ground floor, or maybe this represents a house with a second floor and a basement or no basement. But the point being is that the shower is above or is on the floor above a drain water heat recovery unit. Um, and so in the middle, number two, you see what we were talking about. So you have your drain water going down the gray line to drain, and we have a drain water heat recovery unit installed on that drain line, collecting water from typically the toilet, the sink, the shower, and or bath. And then as you use the shower, hot water goes down. So we preheat the cold water going through the unit and then going and feeding the hot water tank. So that's what we talked about earlier. And that's a very popular, like I mentioned, roughly 60% of the installs out there are being done this way. Obviously, if you have a drain stack that's going through the basement and you have a hot water tank in the basement and the two aren't too far apart, it's pretty easy to connect. It's minimum work and it does the job great. You have another example on number three, where that preheated water, instead of going to the hot water tank, actually goes to the cold side of the fixture of the shower. It could be other fixtures also, but then instead of having cold water come into the fixture, you have warm water mixed with hot water, and so obviously use less hot water. So that's how you can also introduce the energy back into the system. Now, obviously, this mode makes it a bit more complicated because if you want to do 3 or 4 or 5 fixtures, that's a lot of piping. If you want to focus on the shower only, it's fairly simple. So this is something that we do see a little less popular of an option. And then if we revert back to number one, well, you see a combination of both. So the preheat water goes both to the inlet of the hot water tank and also supplies the cold side of the shower head in this instance. Now, someone might ask, why make it so complicated or more complicated? Well, the benefits of that is there's roughly a 10 to 15% gain in efficiency or heat recovery. So for someone looking to do a very high efficient home, what's interesting is when the shower is running, you get maximum efficiency from the device and you're hooked up on the cold side. But if you're using, I'll give an example of a kitchen sink, well, you still have water going to the hot water tank, so you get the benefits of that, but you didn't have to do the plumbing to go to the cold side of the faucet for the kitchen sink, right? So this is a way to maximize efficiency without making things too complex. So these are things that can be looked at depending on the objectives of what drain water heat recovery can do for the specific building. Here we have, again, single family homes, townhouses, things of that nature, where you have multiple showers that are, spread apart, where you don't have a common drain stack, right? So instead of having both showers drain in the same stack, you have a larger home, one's at one end, one's at the other end, but you want both showers to benefit from drain water heat recovery. So these are a few ways that you can do this installation where you might put 2 drain water heat recoveries on those 2 drain stacks and determine a way that makes it practical for that specific house, depending on the layout and where things are located, which make the most sense in terms of plumbing and pipe runs for it to be practical. So these are options that are available and that you can basically pick and choose. Some have some benefits on the efficiency, some have benefits on the installation process. So it's kind of a case by case. Obviously, it's not complicated to determine which one you want, but we're trying here to present a picture of what's available commonly. So it's kind of easy to say, okay, I think I can do 6 fairly easily for my home, and then figure out my savings based on that. Now, these numbers 1 through 6 that we saw, there's a reason for that, and I'll come to it in a couple of slides. So these were single family homes, right? Now, if we look at the small plexes or the stack homes where you have a few stories, like the example I gave a few minutes ago. So if you look at number 7, you have a typical stack dwelling here where you have potentially a basement, ground floor, top floor. And so you see how drain water heat recovery can be installed in that kind of building. So you would install it in the basement, and then you see that the ground floor and the upper floor both drain into that device, and so they also benefit from the savings or the energy recovery uh, in the 2 upper floors. So that's why we were mentioning earlier that you had 2 out of 3, or in the example I gave, 4 out of 6 dwellings that were connected to the unit. Obviously, the ground floor unit cannot drain into the drain water heat recovery because its drain line is below the level of the entry of the drain water heat recovery unit. So this is number 7 is a very typical. There could be a garage below that. That could also be a place where the unit could be installed if someone chose to, and maybe get all 3 dwellings. So there's options there. But number 7, as we see it, very, very, very common. And then you have number 8, which is a variation of that, where we have basically 4 dwellings, and we need a bit more flow rate. So we need more flow to service all the dwellings, and so we typically arrange the units 2 on top of the other, as shown there, and we're able to basically go from a 3/4 inch size line to a 1 inch, and that provides the flow rates required for larger demand. It could also be envisioned that these 2 units could be separated vertically, and one could be on the 2nd floor and one could be in the ground floor. And so now 1 unit services 2 dwellings, etc. And we could also add stories to that building where we distribute drain water heat recovery every other floor, for instance, servicing 2 dwellings. And you just keep going like that. So this is an example where we have what we would call distributed hot water heating. So every dwelling has its own hot water heater. We have an example here where we would have centralized water heating. So maybe we have a building where there's only one water heater servicing. So this setup is more better tuned to smaller dwellings. It's a little harder to expand on larger buildings. So if you have a 40 dwelling building, that needs a little bit of looking into, but these are smaller buildings that are fairly standard. And so if you come across this, these are options that you can apply simply, sort of, without engineering really much of anything. And so you have number 9, the first one, which is, you're servicing 2 dwellings, so just pretty straightforward. Number 10, you might be looking to require a little bit more flow rate. So maybe there's 3 stories there. So you see there's a 1 inch line there instead of a 3/4 inch. So you need more flow rate. So that would be a way to do it. Or maybe you have more fixtures or whatever the reason. And then you have number 11, which if you have basically 2 sets of dwellings side by side that are all sharing, like a six plex kind of building, all sharing the same water heating system. This is a way that it can be done. So this is for the installation. We have a calculator, and the calculator is just a tool for you guys to very quickly select what kind of application you want to be looking at. So we have a calculator where you input very little data and you select a model from what's available in terms of efficiency, and that gives you a basic calculation of energy recovery. This is only focused on showers, so we're not taking into account any other hot water source. Again, trying to be somewhat conservative in the estimates. And then you have the first line here is the configurations that you're going to choose. So you have number 1 here. And so here you basically go down the menu and you decide which one of these images that we saw from 1 to I think it's 12 that resemble the type of building you have and the type of water heating distribution you have and the type of installation you may want. And you just select, let's say number 4. I mentioned number 7 earlier for a 3-story dwelling. You put number 7 in there, and that gives you your results for that configuration. Now these configurations, these images are all in our calculator. So as you look at these images, you've got your calculator just below, and you can tweak around that and come up with a solution very quickly on base models or base configurations. So this is just a helpful tool. Obviously, you guys have a whole host of software out there that can help with that. This is just a help out in getting estimates, I guess.
Yeah.
Maybe selecting an efficiency that you'd be looking for a given savings, or maybe just finding out which scenario, should I install that, which picture is the one for me, and then have that as a reference. So that's the idea behind this tool, is to give you guys with essentially no training or very little training, a sense of what you guys can do. And obviously we're always there to give you a hand with that. So now that we talked maybe how it lays out in a house or a home or dwellings, let's go see practically how that installs. So drain water heat recovery, we manufacture 3-inch and 4-inch sizes. So it's always installed on the main drain stack of, regardless of the type of house. So 3-inch being most common, 4-inch for maybe larger homes or some applications where you have like a MERB or something like that. And they're manufactured out of a 3/4 inch water line, so that's the nominal size. And as I mentioned earlier, we have a little way of stacking 2 units together to get it to a 1-inch equivalent size. If you guys have applications in commercial, I'll give an example. A bunch of showers in a pool project, right? You have 10 showers, and there's things to be done that we can look at with you guys. It installs vertically, so you need vertical space on that drain stack between a clean out and an elbow coming in and a TY or whatever else is on there, or a slip joint, or so you want to have a clean vertical space in which you can install the unit, and you typically need 3 inches to do the installation. So I'll give an example. If you have 50 inches in length, reduced by 3, so that's 47 inches of clean room where you can install it. So you can install a 47-inch unit on that stack. And then you decide the desired efficiency. So maybe you're doing code and it's 42% in Ontario. Maybe it's for an Energy Star project, and if you can get 54%, that gives you whatever you need to get above the target that you're looking for. Or maybe it's a HERS rated home, or maybe you want, the maximum efficiency you can get to minimize the cost of operation of that dwelling or building. So you determine the efficiency and you sort of hone into a model. So I'll show you a table right after. So here we see 2 examples of drain water heat recovery installed on a stack. So you have a basic ABS stack, which is most common in Canada. In larger buildings, you might see cast iron stack. So it doesn't matter. It's a non-issue what kind of stack you have. As I mentioned, installed vertically. It's installed with mechanical no hub couplings, very common. Every contractor or plumbing contractor has access to that, knows how to use it, etc. We usually supply these parts, by the way, with our product. And then you decide what kind of cold water connection you want on it. So would you want a PEX, standard PEX connection if you're doing PEX pipe, or you want expansion PEX if you're doing like the rings that expand, yeah, like the Uprenor type, or do you want just a copper fitting? Then you want to come in and sweat whatever fitting you want on there that you desire. So that's all options that we offer off the get-go. And then in this instance, in the central picture, you see 2 units being stacked. What we talked about just a little earlier. So we We plumb that together, so that gives a 1-inch equivalent line. On the left side, you see a single unit that doesn't have its plumbing there yet, but you see how it's installed on the stack. And just for reference, in terms of a mechanical layout, these units fit in a 2x6 cavity. So they're 4.5 inches in diameter. If you put the connections on the side, like you see in the picture, well, then you can fit that inside a 2x6 wall. So just for understanding the requirements, I would say, that are around that. Drainwater heat recovery, I mentioned length just a minute ago. So the efficiency is, the longer it is, the more efficient it is. Okay. So we're lucky because we, as I mentioned earlier, we have a 4th generation product. So our 42% efficient unit is only 33.5 inches in length. It's a very short unit. And then as we go longer and longer, we increase in efficiency. So the bottom of that graph shows the length. On the side, left side shows the efficiency. So we have a range that's certified under CSA in performance, which is 32 to 62 inches in length. So those are lengths that are very easy to install on a stack. It's uncommon that you have issues to find a space on the vertical stack for most of these units. But that's also why we have all that offering. So you can choose any model you want, any length you want in there for the efficiency that you desire. And so they'll run from 41 and all the way to 57 change in efficiency. And that's a 3-inch size, a 4-inch size. We go a little higher in efficiency. But that's just give you guys an idea that, you know, if you're looking for ballpark 50% efficient unit, you're looking at a 47-inch unit. So it's 4 feet. So again, just to put things in perspective in your minds. I mentioned CSA performance verified under the CSA standard. So this is kind of thing we'll publish. Has been third-party generated, basically. And so you have our model numbers, and you have the length of the unit, and then you have the efficiency, and that's always at 2.5 gallons a minute. Now, maybe a note here is to keep in mind is that 2.5 gallons a minute, these standards were made 10 years ago now. And so we see flow rates for shower heads being much lower than that today. And so as you reduce the shower flow rate, you actually increase the efficiency of the unit.
Interesting.
You don't increase the amount of energy necessarily that you take back because you use less, right? But you get more of it back.
Yeah.
So that's something that could be considered. But this is the data how the standard expects us to publish the numbers.
I see.
So,
That's interesting.
Yeah. So you have the efficiency, you have the pressure loss at the same 2.5 gallons a minute, which is fairly low. So, and then your heat recovery rate and kilowatts. So that's like instant. So if you run it for an hour, it'd be in kilowatt hours. So as I mentioned earlier, I was talking 8 kilowatts earlier, and then I mentioned 10 kilowatts. So you see the range here from 7 to 10 something. So this is information we publish. So if you're looking at different models, there's highlighted in yellow some of the popular ones that we always have on stock ready to go. But as a manufacturer, we turn everything around in a day or so, so it's never an issue in terms of selecting any model that you guys need for your application. So Intertech certifies our units, again, under the CSA B51 and B52 standards, which is a combination of performance, so energy efficiency, not energy, pardon me, percentage of energy recovery under given conditions, which was the 2.5 gallons a minute I talked about earlier, and also construction standards, so how it's built and pressure rating and that kind of stuff. So I won't touch base on it. I'm just letting you guys know what's out there, and then Nick is going to take over in a few minutes with some examples. But drainwater heat recovery has been around for a while now. Is integral to the Hot 2000 software. So there's a, if you look under the domestic hot water tab, it's there. You click it, select a model number, type installation, and then you get your savings in there. And so it's pretty easy to integrate and get the before and after. For the folks in the States, Rate, EcoTro also integrated in those two softwares. So something that you guys can look at. Again, fairly easy. You click a couple of clicks, select the percentage of recovery you want, and I'll give you the results. For Ecotrope, we're looking roughly at between 1 and 2 points. For a HERS rating of roughly 63, 65. So you can get 1
Okay.
easily, you can stretch it to 2.
Yeah.
Depending on what you're looking at, and obviously smaller homes benefit a bit more. You might get the 2 points in a smaller home than a larger home. So just to give
Yeah.
you a ballpark figure here, and you guys can go out there and test it out. Um,
I'm just going to jump in there, Mark, and pose our next question. I guess what is holding people back from installing drain water heat recovery? So let's just see what that results in.
Yeah, that's an interesting question. Good for you folks for asking that, though. Not a lot of manufacturers would want to get that information.
Well, we like to know what we can do for our industry, right? What we can do for the plumbers, the builders, and everyone. So this is an important one for us.
And I think it's interesting, and I'm not surprised of the last one, that unsure of the ROI, right? It's hard to sort of take in, to figure that one out, I think, for a lot
I
of
think
folks.
because it's so simple, we just don't know. People just look at it and it seems so simple that it's say, it can't work, it doesn't work, or how does it work? So that's one that I think is pretty important to address is the ROI there, and how can I get my ROI to the best it can be.
Oh, that's interesting.
Did you
So
look
does
at
that
that?
sort of fit with what you, Mark, with you and Dylan sort of thought?
it's kind of I guess where we thought it would be. Upfront cost. I mentioned a little bit of cost earlier, and I was trying to put something in people's mind because we get a lot of different things from customers coming back, and sometimes it's way out there. It's not necessarily real data, and so we do a lot of builders that do 400 homes, 500 homes, 600 homes, etc.
Right.
And we talk to them. So what are you guys getting charged? So we try to get some sort of an idea of what's out there. So as I mentioned, I think the cost of it has gone down through the years, even despite inflation, and it's more affordable today than it was in the past. And in
Yeah,
terms of ROI, the thing is, it's kind of difficult to, unless you take out your calculator and start figuring it out. So it's not something that's maybe as easy to figure out. But then you have to ask your cost of energy, your efficiency of your hot water system, et cetera, et cetera. So
Yeah.
I'm not saying that our calculator has all the answers, but it collects some of that data for you, gives you some results that you can apply to your case and to your
yeah.
cost. And so
Yeah.
we
I
sort of
was
go from there. Maybe
I
one
was
note that's quite
sorry, Mark.
interesting is that rainwater heat recovery works as you use it. So the more you use it, the more you save. So obviously, if you have a scenario where you have a one person, let's say an elderly person living in a home, and you want to use rainwater heat recovery in that scenario, the usage is very low. And so, but that's true with any and with
Yeah.
all other, if you look at a high efficiency hot water heater,
Yeah.
it's not being used, so it's not saving that
Yeah.
much, right?
That's right.
And if you have another case where you have 5 people in a family home, with well, I've got a lot of daughters, so I can maybe speak to that.
Well,
And usage is
yeah.
where you get all your benefits, right?
But Mark, it's interesting, right? Because with building science, we do have to look at return on investment, right? Or let's say, and that's true. And then the cost of the application. But with building science, we also have to look at the actual impact on the person. So you have your daughters, we have our family. aside from the return on investment, we know that technologies like this actually provide more hot water. That is a comfort thing. That's something that you can't put a number on. And I think that's something that we always have to be very careful of when we start to look at technologies or the way we build, is that we all want to jump very quickly to the ROI, and it's true because affordability and practical installation. However, when the consumer engages, we're going to have to be ready to translate these other benefits to them as well. Like when the Odings heard in our house 12 years ago that if we put one of these units onto our air source hot water tank, that we could shower all day long and it would stay in heat pump mode, that was sort of cool. And it was even more cool when we found out it actually worked.
Well, obviously, you know, we're kind of inclined in the energy efficiency side of things and looking at that all the time. But as you just mentioned, that's definitely a side benefit that we get. And as I was maybe mentioning earlier, is the fact that, you know, the fact that you'll never have to service that thing or put a dime into it. That's something to consider as a homeowner, because you know how it costs a lot of money to service a whole bunch of items that you have. I'll say mechanical devices in a
That's right.
home. Between maintenance and service and replacement, right?
That's right.
And so that's also something that I think needs to be considered in terms of, you know, lifespan benefits.
Good.
That device.
Good, good. Are we okay to move on to Nick, or you got some more slides, Marc?
No, actually, I'm good to go with Nick. We were getting at the end of this.
Okay, good.
Perfect.
All right. So we'll stop sharing on one side and get Nick up on his side. So I think what Nick has done is worked a little bit with Marc and Dylan, but maybe more importantly, Nick has worked with a number of our builder clients, community scale and otherwise, and has actually developed a little bit of a case study, if you will, and the impact of the technology. So, yeah.
Yeah. Can you hear me all right, Andy?
Yeah, we can hear you good. Yeah, take it away.
Perfect. Yeah, so like Andy said, we wanted to just put together a little bit of a case study, more of a representation of sort of how this works in a real sort of house with a bunch of different scenarios. So we chose a single detached home to look at, a little bit larger, so 2 stories with a basement here, north facing, about 32,000 cubic feet of volume and 3,500 square feet, so a bigger home. 3 bedrooms, 3.5 bathrooms. And what we did was take this technology and apply it in a bunch of different modeling scenarios. So we looked at 3 different locations, those being Toronto, Ontario, climate zone 5, Calgary, Alberta, climate zone 6, and Chicago, Illinois, for our American friends in climate zone 5. And we also wanted to take a look, Marc mentioned that this technology can be used with various different hot water systems. So we wanted to look at all of those scenarios as well. So we have a natural gas tank, very similar to what you see in the SB12 Ontario code requirements there, a 0.67 efficiency. We also looked at natural gas tankless at 0.95 EF, an electric tank, 0.9 EF, and then also heat pump water heater, which we're seeing used a lot in our net zero homes that we're working with. And that's up at 3.88 UEF. Using one of these thermal drain units, the one that Marc was talking about, on the higher end of efficiency there. This is the 60, I believe the 62-inch model, and it's an efficiency of 57.2% at 9.5 liters per minute, or that's, I believe that's that 2.5 gallons per minute. And then just looking at the metrics, we're looking at total energy consumption in gigajoules for our Canadian locations. So gigajoule, for those that don't know, is a fuel agnostic measure of energy. So that takes into account kilowatt hours and cubic meters of natural gas burned. And then we're looking at HERS rating for Chicago. And then in both locations, or all 3 locations, we're looking at total greenhouse gas emissions. So again, seen this many times here. And then just to lay out sort of the different modeling specs that we were using here. So we used in Toronto, we used the standard OBC package A4. In Calgary, we used NBC 2020. And in Chicago, we used the IECC 2021 with the regional amendments to the best of our abilities there. These slides are going out, so you can take a look at these later. I won't go into too much detail.
One of the reasons Nick and team use the IECC 2021, for those of you working in the US, is because obviously many would know the 2020 IECC is being adopted in multiple states, and it becomes it's very close to zero energy ready. Not quite there, but very close. So we find technologies like this can be very impactful.
Yeah, thanks for that, Andy. And just wanted to touch a little bit on emissions before we get into talking about GHGs as well. So here we just have a breakdown of the different provinces and territories and their current grid emissions. So that's the GHGs that are coming from production of electricity in these different locations here. And they're categorized into sort of high, moderate, and low emissions factors. So Alberta, currently has a high grid emissions factor of around 800 grams of CO2 equivalent per kilowatt hour. Ontario is a moderate grid, and then Illinois also is a high grid emission factor. That being said, the 2025 version of the MBC has an inclusion PCF 2026 that is looking to look at how these emissions factors are sort of evolving over the next few years. And we can see at least, I'll just highlight Alberta for now, is projected to be quite a bit lower grid emissions by 2030. So they're really doing some work to improve the cleanliness of the grid.
Yeah. And notably, those of you in Ontario, you notice that the grid emissions are actually projected to go up. So I think it's the only province north of the border that actually has projections to go up. So to Nick's point, we model based on today, but think about this, that the models are done for today, but as the grid changes, the model will change as well too. So keep that in the back of your mind.
Exactly. So here, we've just broken down the total energy consumption on the left here, and then greenhouse gas emissions on the right. So this is for Toronto, again, in Ontario, climate zone 5. So we've shown the 4 different hot water heating systems here. So the electric tank, heat pump water heater, gas tank, and gas tankless. The solid line shows the energy performance with the domestic drain water heat recovery. My apologies. And the hatched line is without the drain water. So we can see, depending on which system you're using, we're looking at about a 1 to 2 gigajoule reduction in energy consumption. And because of the grid emissions in Ontario, we're not seeing too much of a reduction in greenhouse gases in this scenario, in this location. But that energy consumption is pretty significant there.
One thing, Nick, I think just to note for folks, because I see some questions in the chat or in the Q&A statements about, it depends on how many people are in the home. And that is absolutely true. So one thing everyone needs to keep in mind is when we do modeling like this, even in the US or Canada, the reference is the standard operating conditions that are assumed by the building code. So for instance, in Canada, we can't just willy-nilly change how many people we think are in that unit. So the Building Code of Canada tells us that when you model a home, regardless of size, for the most part, that it's going to have 2 adults, 1 child in the home 50% of the time with a standard showering and flow rate of such. So that's something that we can't modify. But to Marc's point, if you know that there's going to be more occupants in the building, you can go to a tool there that they have on their site and model that. So just to be clear, the assumptions here are based on the building code assumptions about occupant behavior, which are pretty, I'm going to say fairly lean. in
Yep.
some ways.
For sure. Yeah. Okay, so moving to Alberta here with high categorized grid emissions. We're seeing the same two graphs, the same modeling scenarios here. And instead, we're seeing around a 1.5 to 3 gigajoule reduction here, and 0.1 to 0.5 tons of greenhouse gas emissions reductions as well too. So not an insignificant amount of reduction here as well.
Not at all.
And then moving into Chicago, Illinois. So a little bit different here. We have the HERS rating along the y-axis here, and imperial tons of CO2 equivalent shown here on the right as well too. And as Marc mentioned earlier, depending on geometry of the home and occupant loads and that sort of thing, we're looking at around a 1 to 2 HERS reduction. And again, a 0.2 ton of GHG reduction as well too, depending on the system that you're using there. So something else that was briefly touched on earlier, and I saw in the Q&A section as well too, somebody was asking about the sort of trade-off of the embodied carbon and the operational carbon as well too. So far, we've mostly just been talking about the operational carbon savings and that's coupled with energy savings as well too. But looking forward into future codes, upfront embodied carbon is something that we'll also have to start considering as well. So this graphic here just shows a little bit about the difference between the two. So operational carbon is that comes from the direct operation of the building. So that's space and water heating for the most part, and then also electricity usage as well. So that's the emissions associated with the generation of the electricity used in the home, as well as burning fossil fuels to heat space and water as well too. So that's operational carbon. And then when we talk about embodied carbon, it's the emissions associated with the sort of manufacturing process of the materials themselves. And what we have included, or what is included in those estimates, are what we call stage A1 through A3. And so that includes the raw material supply, transportation, and the manufacturing process. So we've actually gotten information from EcoInnovation on their materials. They had sort of a preliminary study done on the materials used for their product. And so they passed that along to us. And for that 62-inch unit that we were talking about in the previous models, there's an estimate of approximately 72 kilograms. So kilograms, not tons, of CO2 equivalent. And that's the upfront embodied carbon associated with this unit here. So something that we like to talk about, I'll just go back a slide actually, is so Marc was mentioning the financial ROI of this product, but something we can also consider is the embodied carbon payback period. And this is essentially a measure of how long it takes for the operational carbon savings to pay for the upfront embodied carbon of the materials and manufacturing itself. So we know that this technology is saving us in operational carbon, but there is that cost of all of the mining of the materials and transportation and manufacturing that has to be offset, if you will, as well. So what we did was take Alberta as an example, and we did all 4 of those hot water scenarios and estimated based on the operational carbon savings and the upfront embodied numbers that we got from EcoInnovations. We looked, and this is again assuming a static grid emission factor that was shown in that few slides ago. So the current grid operation emissions. And so for an electric tank in Calgary, we see this embodied carbon payback period of less than 1 year, so 0.1 years. You can barely even see this blue dot here, but that's that 0.02 or 0.072 tons of carbon emissions being offset with its savings after, yes, less than 1 year. If we move to our heat pump water heater, again, we're seeing that embodied carbon payback of 0.6 years, so less than a year before the savings is paying for itself. Interestingly, if we move to the gas tank, we're seeing this embodied carbon payback period is drastically increased out to about 15 years. And this just has to do with, and you can correct me if I'm wrong here, but this has to do with the emissions of the electricity grid in Alberta.
That's right.
So we're looking at the electricity, obviously because of the high emissions factor of the electricity, those savings are a lot more, count a lot more towards operation.
Yeah. And it is interesting too, when you look at something like that, you know, we would like to think that we could use a material that would have I'm going to say a emissions balance point between operational and upfront of no more than 5 to 6 years. And again, that's just a notional number that some have talked about as being ideal, that or less. But I also want to throw into this that this is also a technology that once it is in the home, it doesn't need to be replaced or repaired at intermittent schedules, right? It's not going to be a window that at 15 to 20 years is replaced, or a furnace or a heat pump that's going to have to undergo replacement as well. It will really have a true span of 30 plus years as a passive fixture in the home. So anyways, yeah, it's really, really helpful because we look at something that's bright and shiny and it's copper and surely it's going to have a lot of and it's like, well, hold on, like, let's do the numbers. Don't lose sleep over this. And lo and behold, actually they tend to make sense. So, yeah.
Yeah. And again, it is a product that is 100% recyclable at end of life as well, too. So that
Right.
is something to be considered as well, too.
That's right.
When we're talking about embodied emissions. And then just last slide here. In this situation here, we're talking about gas tankless. Again, we're looking at that embodied carbon balance point of about 17 years. So in this climate zone, in this sort of configuration, potentially doesn't make sense from this embodied carbon perspective here.
Good.
And then lastly, we'll just talk about just a couple of minutes here. I know we're running short on time. Just I think Marc sort of already mentioned this, increased recovery rates, especially we're seeing when paired with heat pump water heaters, which tend to have a bit of a lower recovery rate, about a 30 to 40% increased rate. And then something that we talked about, or is in the title of this webinar, is using this technology in sort of net zero ready homes, where every gigajoule definitely counts when we're talking about these low load homes, especially if you're going the net zero route. 1 to 2 gigajoules that we were seeing in there could be the difference of 1 to 2 solar panels getting to that offset there. Again, looking at Energy Star, if you're using this this unit here, the 57.2% efficient unit that we were talking about, that gives you, if you're familiar with the builder option package system with Energy Star, that gets you about 0.4 points, BOP points. That is at a much lower price point than saying upgrading to a full R10 under slab insulation, which only gets you 0.2 points. So pretty significant savings there, and can really assist in these programs, as well as energy reduction and GHG reductions in programs such as the MLI Select program. I know we've used this technology a lot to help out our builders in achieving those affordability programs as well too.
Good.
All right, I think that's it for me.
Thanks, Nick. No, that's very, very helpful. It's always good to look at a practical application on that, something we actually build, isn't it? So, and the one slide, again, we sort of wrapped up with that last slide that shows the drain water combined with an air source hot water tank. And we know that that is a technology that's probably more familiar to some than others. We know that it's, something that in climate zones 4, 5, 6, 7, we're only now starting to see it, but it is starting to come to play, right? And the hot water load is a big load that we're going to see start to change over the next few years. And it's interesting when we see technologies that actually work together. One of the concerns that North Americans have, and we'll just be really blunt, is any type of electrical hot water heating has always meant in the mind of most North Americans that they're going to have less hot water because we're used to that high gas combustion based generation of heat. We got hot water and man, we got lots of it now, right? We got a tankless condensing unit sitting in that basement and it can put out 190,000 BTUs. Like, let's go, right? We want showers, we want lots of hot water. And so we do have to understand, as much as we would say, well, we need to change lifestyle, that's asking a lot. But I think it's good to see technology combinations like this to go, wait a minute, you know, we can have our cake and eat it too if we use the right kind of technology tie-ins. Let's get to some questions. So Dylan, you've been in the background answering some questions. So folks, please take a quick look at the Q&A. You'll see Dylan's answered a number of questions in there. And Dylan, I think we've left a couple, you said you got a couple ideal questions.
Yeah, I've left a couple for you guys. I mean, I don't know if you want to pose them, Andy.
Yeah.
I think we can go with, I think we can just run through this list.
Okay.
Yeah.
Let's start with that. I'm gonna cherry pick just because I get to do that as the host. So let's just do a couple things. I did see one note on here. I think it's been taken off. Someone mentioned that drain water, I think you'd answered that, Dylan, and I wanted to cap that one too, that drain water had been taken out of the Ontario Building Code. It actually has not. It is still a requirement under prescriptive, but it is not a requirement under performance. So nothing has changed in Ontario to that point. Now that may change again as the province would start to look at the new 2025 National Building Code, which again, the province then has 18 to 22 months from that point in time to consider harmonization. Okay, we're going to start here, and let's start in here with the first one we've got. I'm going to jump in with Mosin here. Time is a key factor in heat transfer. Says, in the context of drain water heat recovery, the wastewater flow is not steady, and it takes time for the drain pipe to heat up. Are there any mitigation strategies to reduce that transient effect? That's an interesting one, Marc. That's a little deep dive.
What's nice is that I'm also the guy at EcoInnovation that does all the testing inside. So I have the answers to that question. So typically the heat up process for a thermal drain unit, which is all copper, we usually get it up to temperature in 30 seconds flat. So 30 seconds of hot water going down the drain, we go from room temperature, so let's say I'll call it 20 degrees, and then up to operating temperature, which might be in a 27 or so. Obviously, the bottom of your unit is cold and the top of the unit is warm, so it's different, but what we would call the steady state. So
okay.
when we're done ramping up temperature and we're steady state, it's 30 seconds. So if you can imagine, you've got I'll say a 10-minute shower, you've got 30 seconds of ramping up, where you do get some heat recovery as you increase the temperatures, and then you hit that steady state where you have basically 9.5 minutes of steady state recovery, after which you shut off the shower. So that's what happens physically in the device in the unit.
Nice. No, that's very helpful. Next question. This was an anonymous attendee. Question was, and again, this is sort of an interesting one. Does the cooled drain water have any positive attributes?
Does the what?
The water that's cooled. So instead of sending warm water that has more embodied energy in it down the drain system, is there benefits to it being pre-cooled before it move on?
Well, is it a benefit, or I would say we've had applications where we do things like restaurants.
Oh yeah.
Okay, and they have issues with the water being too hot when they send it off. So we do some cooling in that, where we recover the heat, obviously, but that has the positive effect of dropping the temperature from a dishwasher type, which is superheated, and reduce the temperature of it, so that they're allowed now to reject, because otherwise they have to mix in cold water flow through the drainage to reduce the temperature. So so that also saves on water if you're metered. So that's something interesting. And we've been known, this is really out of the beaten path, but to do stuff with steam, low pressure steam, to try to
Yeah.
condensate some of that. And
Yeah.
but that
Yeah.
again, off the beaten path. But
Yeah.
just so it's a heat exchanger. It'll work
That's right. Yeah, that's cool.
regardless of what you're trying to do, increase or decrease.
We had another question Mohsen asked, and I think you covered this, and so did Nick. So maybe this has been answered for Mohsen, but again, he just had that question about the energy savings associated with using drain water when it's combined with either natural gas, combustion based, or electric. And so he asked for some data. So obviously, Mohsen, the slides and everything you've seen today will be provided to you. Marc, Dylan, I don't know if you want to comment anymore, if there's any additional data that you could provide on that, or.
Well, I can maybe give information, give a view of maybe stepping back a little bit. So I'll give an example. You have a 67% efficient water heater that's code. So now you say I'm going to bring it up to like a 95%. Okay, so now you've reduced your heating load, right? So what do you do next? You say I'm going to increase rainwater heat recovery, and we talked about efficiency. So let's say we're able to get a realistic in a home. The whole complete usage, we can easily get 35, sometimes up to 45% of the hot water energy load. So now wherever you're at with your energy load for your hot water, you can say, well, I'm going to take 35% of that load and I'm going to reduce it by combining it with rainwater heat recovery. And so that, again, ballpark figures, and that's where the calculator comes in. So if you go to our calculator, you put your usage in, and we'll tell you how much you can draw down from that based on the efficiency of your water system.
Nice.
And your shower head flow rate and your consumption. So that's a way to look at it. Now there's other ways to look at it, and
Sure.
if you're using some kind of software, well, they'll give you the numbers. Like Nick showed earlier, it gives numbers from the whole house. So
it is interesting. The one thing I liked about your little calculator is when we get into existing homes and retrofit, right? That's the really big nut to crack. And this is not a difficult technology to implement in some cases in retrofit scenarios in homes. So I'm just speaking of homes. But in an existing home, you actually would have a better sense of what the hot water usage is.
Yes, well, obviously, if you're looking at an existing home, looking to retrofit, and you know the occupancy of that home, and you know the type of equipment that it's installed, and then obviously it's kind of easy. It's not going back to the code.
That's right.
Usage, right, where you're kind of stuck there. So obviously that's different. And just for reference with retrofit, the only difficulty that you usually run into is access. Now, if you have access to your plumbing system or drain pipe, it's a very simple thing to install, right?
Right.
So that's the assumption that you would make is access. Aside from that, no problem.
And it seems like there are some questions before to Dylan, some conversations that some municipalities do want there to be some access to, so you can't just bury it in a wall and hide it, that depending on municipalities and jurisdictions, some may want a little bit of a door there or something that just so you can access.
There'll be all sorts of stipulations surrounding drain water, certain efficiencies, certain accesses. So we always suggest looking at your municipal code to make sure that you're following the procedures properly and the usage properly.
I'm going to move through pretty quick. We're at 2:35. We'll take one. John Breckelman's, would insulating the drain water heat recovery unit and the hot water return line bring any benefit?
So the answer, we looked at temperatures earlier, so that's why I put that there. So we're looking to increase the temperature in the winter time from, let's say, 10 to 21 or from 10 to 25. So you're usually around room temperature when you're preheated or just above. So insulation sometimes is not cost effective to do. The unit doesn't need to be insulated, doesn't provide much benefit. Unless you want to mitigate some sort of a cold sweating of the unit if it's in an unconditioned space where it shouldn't be. And so pipe insulation is not a bad thing. It's not a huge benefit because the temperature difference between room temperature and the preheat temperature is not very large.
Yeah.
And also, if you're using PEX pipe, which it has a fairly low heat transfer coefficient, it's less of an issue. Now, of course, compared to a hot water pipe where you're running at 60 degrees Celsius, so that's 40 degrees above room temperature. There's more potential savings in that case.
I think I'm gonna have to wrap up, folks. What we're gonna do is we do have more questions from Zoran, Ken, and a number of others. We're actually gonna get those questions to Dylan and Marc. We're gonna have them answer them, and we're gonna publish those when we send them out, if that's okay. So that would, if that helps. So I'm going to real quick. I know there's one question Zoran asked, and it's not really tied to drain water recovery. And it just happens to be a question that was asked recently, and we did some analysis. The question was, you know, the HERS rating, which is US based, how many builders, energy raters use it in Ontario percentage wise? In our analysis, it's less than 3%. I'll be very frank. We use the rating systems Ecotrope REM for the US based. In Canada, we have been challenged in some cases legally because the HERS rating system and those softwares actually use US based algorithms. They do not use CSA based algorithms or ULC based algorithms. So again, the outcomes are going to be very similar, but Zoran, just to answer your question, we don't see a lot here again because it doesn't really reference Canadian standards. But glad to talk about that another time. So Ken, the rest, we're going to send out some answers to your question. I think there's a last poll there. Would you consider using drain water heat recovery? I think that's a fair question to ask. I love the fact that we revisited a technology that many of us, like I said before, are very familiar with. But now it seems like we're, you know, as we get to the thin edge of a wedge of trying to make homes more efficient, we're having to get back to technologies that are sort of tried and true. I'm just going to share a couple of things with you folks before we wrap up. I know the holiday season is coming this next year. We do have another season, Critical Canadian Building Science season, that's going to be coming up. And so wait on that. We've got probably about 12 to 15 sessions that are being planned on all sorts of different topics and subjects. Also, please keep in mind our Building Science Digest just went out. If you didn't receive it, let us know and we'll get you on the line. Outside of that, I do want to thank Enbridge again for their help and sponsorship, but I want to give special thanks to Dylan, Marc, and Nick. You guys did a phenomenal job and got techie, but not too techie, and it was very helpful. So thank you so much.
No worries.
Thanks for having us.
Yeah, good to have you. And to the rest of you folks, happy holidays. Hope everyone gets some good rest over the coming holiday season, and hopefully we'll see many of you in the new year. 2025. Are we already into the 2000s by a quarter of a century? Anyway,
Crazy, isn't it? Crazy.
All right. Thank you folks very much and have a good week.
Happy holiday. Bye.